Yeah, so I'm going to talk about having fewer transaction conflicts. And the reason I was working on this problem is that I had a table downstream of 700 upstream tables. Anytime anything upstream changed, I wanted to propagate the changes to my downstream table. And so there could be 700 processes writing to the same table at the same time. They started running into each other. Okay. Databricks supports transactions, which is great, which is basically saying, okay, do all of this operation or none of it. So you're never going to have a write which says update these 10 rows and 7 of them will be updated and 3 will not be. That would be terrible to debug. So fortunately, we can in fact do this. When you have concurrent transactions, there's kind of two mechanisms various database-like systems use to manage concurrency. The first is asking for locks. So saying, okay, I want to update this type of data and give me the exclusive permission to update this type of data. Don't let anyone else update it while I'm updating. The second is optimistic control, which is that we welcome everyone to try to do what they can, but we have some system limitations in place that will cancel some ongoing transactions if we feel like we can't do it safely. Databricks uses the second type, so there are no locks. In many cases, this is really good, because many times, only one process writes to a Databricks at a time because you're doing updates in batch. It's not like you're going to have various Databricks processes writing one row at a time. You end up with millions of files, and that's 3 bad things would happen. So, in most cases, there are few writers, and so optimistic control saves us the hassle of having to get locks. However, in my case, I did have 700 writers, and this led to many concurrency issues. Databricks has very good documentation on concurrency. I will just note that in my talk, update will mean update or delete, but I have some exceptions for merge into. Okay, so the way this talk is going to be set up is I will have 3 notebooks for a lot of examples. One notebook will be about setting up some tables as a starting state. That's going to be the notebook at the bottom. I know you can't read it, don't worry for now. Then there's going to be 2 other notebooks, which are going to represent 2 transactions I will try to run at the same time. And we will try to see what happens when I run those transactions at the same time. For most of these, I've pre-recorded myself because trying to click something exactly at the same time with the internet and stuff is very annoying. So rather than me having to try and fail many times, I avoid that. But for the first one, it's very easy, so I will just give you a sneak preview of the sort of thing that is going to happen in each of these. And that way I can actually make it big enough such that you'll be able to look at the text. So really, we just have a setup step, creating a table and replacing with a fresh state. In all of my tables, there will be students with IDs and names. Later, they'll start having colors, favorite colors. And that's really all the setup we need for the first step, where we're going to try to run 2 inserts at the same time. So here's transaction 1. It inserts a new student. that the student was written twice from each transaction, and that in the table history, we'll see that there were 2 writes. This is the initial table creation, so these are the 2 writes from the transactions a bit later. They happened at about the same time, but really it didn't matter. So inserts are very safe, is what I want you to take away from this in terms of concurrency. They don't do any reads, they don't conflict. Life is good. So life starts being a little bit more complicated once we get to...
In the second example, we're again going to start with a table with 2 rows. And the transaction on the left will try to, again, insert a row, but the transaction on the right will try to change all existing rows, change all the favorite colors to violet. So let's see what happens when we try to run these at about the same time. So both of the transactions succeeded. And you'll actually notice that this one only affected 2 rows. So in a sense, you might think, oh, maybe this just happened before the transaction here, and the table state would be consistent with that approach. So these 2 were changed their color. The added row was not. But interestingly, if we look in the table history, sometimes it'll show that the update happened after the write. So this is a bit of an odd state. Because it looks like what actually happened was that the read part of the update happened before this write, but the write part of the update happened after this write. So this idea of history becomes a little less well defined. In this third example, we're going to try to use this idea of a serializable isolation level to remove the indeterminism we had in the previous example. We have the same operations, so the transaction on the left tries to insert a row, the transaction on the right tries to update all existing rows, and we're going to try to run these at about the same time. And in this case, we see our first example of a concurrent append exception, which is basically Databricks telling us, I cannot do the thing that you wanted me to within the constraints of the current isolation level. There is no way to do the thing that I was trying to do, running the transactions one at a time, based on the state that they were in together. And if we look at what happened in the table, in fact, the insert happened, but the update did not happen at all.
So this is where we start having this idea of isolation level. And the default one in Databricks is quote-unquote write serializable, which basically means that the writes can be orchestrated in some order one at a time that produces the same result as if we ran them at the same time. But we can make it more strict so that the reads also start being subject to this constraint. And that's what we see here. So you kind of have a choice. With write serializable, maybe your history will be a little messed up when there's some reads involved. And with serializable, you will sometimes get some crashes because we cannot run a transaction and you'll get this exception.
In the fourth example, we are going to have 2 updates running at the same time. And in fact, they will try to change my favorite color to 2 different things. So this is back to the base table with write serializable isolation level, not serializable. And you'll notice that this time we still get a concurrent append exception. So there was no way for these 2 transactions running at the same time to have the same result as if they were run one at a time. And so you'll see that the transaction on the left does not do anything, and my favorite color ends up being violet. In this fifth example, we're again going to try to have 2 updates at the same time, but this time the 2 updates will be modifying 2 different rows in the table. So let's see what happens when we try to run these at the same time. And in fact, we still get a concurrent append exception. And what happened is when we created this table, these 2 rows were written to the same data file. And the default operation for both of these operations is to read that file and change the value of this and rewrite the new file, but the file has both data points. So they were actually trying to both operate on the same file at the same time, and that's how we still get this concurrent append exception and only one of the transactions goes through.
So in the first of these updates, I would naturally expect a fail because there is very explicitly a set of things that conflict. So really, we are trying to change my favorite color, and we're trying to change it to two different things. That's a reasonable semantic conflict. In the second one, it's actually a constraint of internals of the system I probably don't care about. So because when we did the initial write, we wrote to the same file, and that data is in the same file, to edit either row, by default, we're going to read that file and rewrite a new version of that file. So we want some way to avoid that, so that when we have updates which touch different rows, they should still be able to succeed. And there's two main paths at that. The first is using partitioning. What partitioning does is puts data in different files based on some field in them. So that's what we're going to try to do first.
In this next example, we're going to use the idea of partitioning to try to fix the file problem in the previous example. When we partition a table, one of the things it does is guarantees that rows with different values for the partition will be written to different files. So let's see what happens when we try to update these two rows at the same time. And we'll actually notice that we still...
So you'll notice that I tricked you. So even though we partitioned and wrote them to different files, these SQL statements don't know that. So they have to read both files in order to figure out what the data is, because I didn't specify a partition column in my SQL query. And so even though the data is partitioned, the SQL file doesn't know that. One of them gets changed. We again have a concurrent exception. So the way we actually need to fix it.
In the seventh example, we're again going to try to update these two different rows at the same time, but this time we're actually going to specify in the SQL query what the value of the partition is. And now we'll notice that actually both of the updates do succeed. We can look at the table contents to see that, in fact, both of the colors were changed. And the idea is that by specifying the value of the partition in the query, we no longer need to potentially read both of the files in order to know what to update.
Okay, but so that was approach one, basically use partitions and specify the value of partitions. Partitions don't work well with some Databricks features, for example, liquid clustering. So for about a year, we had this solution in place. And we wanted to speed up the reads on the table. And so we looked for a different solution. And to do that, we need to start talking about deletion vectors. So that's going to be up next.
In this eighth example, we're going to try to use a different approach to solving the problem of not having to rewrite the whole file for a row. We're going to use deletion vectors. And what deletion vectors do is that updates no longer rewrite a whole file. Instead, they write some metadata about which rows should no longer be read from that file and should be read from a new file. So again, we're going to try to write two updates at the same time. And we'll see that, again, this was able to succeed. So this is a different approach to being able to update different rows in a table at the same time without necessitating the use of partitioning. This can be nice because maybe you want to use liquid clustering, which is not compatible with partitioning, and if you use deletion vectors, you could do that. In this ninth example...
Okay, so now we're going to move into merge intos. An interesting thing about this example is, and let me actually get the code so I can zoom in on it. inserts, again, running. But because the inserts are going to be parts of merges, they will no longer never conflict. So the type of query we're going to be having here is to look at some source of data, but the only condition that we'll ever do is if there is a new row, then we'll do an insert. So before, you might remember when we ran 2 inserts at a time, we could not conflict. This type of insert can conflict because in the time that the statement is running, some other data could have been written, so the read part would conflict, and so the whole transaction conflicts. So this is, I'm not going to bother playing the video of this one, but the idea is that we can get a conflict between this identical transaction trying to insert a single row into the table. So deletion vectors are not something that helps with this type of thing, and what we can do, however, is to use both deletion vectors and
in this 11th example, we again have deletion vectors enabled, and we're going to try to have 2 simultaneous merge intos. But this time they're going to...
right. So if we insert a different row, before we were still trying to insert the same row from two transactions. A deletion vector is going to allow us to do it when it's 2 different rows. But there's a bit of a limitation, which is that the SQL query itself needs to be able to know that the row we're trying to insert in one of the transactions is different from the row we're trying to insert in the other transaction. So here, this row is clearly different from this row, and so the inserts can happen at the same time. Interestingly, if we make it a little bit more obtuse and we put them into an array, you can no longer tell just from analyzing the SQL statement that these will not conflict. And so there's this very interesting behavior where...
In this 12th example, we are again going to have 2 concurrent merge intos writing to a table with deletion vectors. And they're going to insert 2 different rows. But this time, unlike in the previous example, the way they get these rows is through exploding an array as opposed to an ID being explicitly specified. So this time, one of them does fail, because looking just at the outer SQL, it is not obvious to the SQL parser that these 2 will not touch the same row. Now,
basically, the idea is that a row-level concurrency needs to be able to tell just from the query itself, rather than the results of the query, that 2 of the same rows will not be touched. So we cannot have it run SQL first. Okay, so let's go back to the problem I was trying to solve, where we had 700 upstream tables writing to the same downstream table. And what we had initially was 700 merge into statements. And you saw how the merge intos can conflict quite capriciously, where even if they don't conflict by rows, because the result of the query, there's a result of a SQL query necessary to tell that, we can't do it. However, inserts themselves are pretty cheap and don't conflict at all. So what we really did was just make a new table in between, write all the potential changes we would have to that table using inserts, and then use a merge into using the change feed from that table. So that also has the nice ability that we get to batch updates from multiple tables into the intermediate table when we try to merge them into. So that's our current implementation of this problem. That's all I have.